Now it's time to have a look at what the number e really is and where do we get it from and what happens here. What we want to do is in this topic is derive and integrate exponential functions and logarithmic functions. Get that out. So what we want to do first is have a look at where does e come into play. So one we haven't found derivative of before is this one, y is equal to 10 to the power of x. Now, if we go and do this from first principles, so remember our first principles, the limiting function as h approaches 0 of the rise over the run of a function. So we've got the function of x plus h, so 10 to the power of x plus h, and minus 10 function of x, which is 10 to the power of x, all over h. Again, h is approaching 0, so we can't just start subbing h being equal to 0. If we factorise here, we get 10 to the power of x, because that's common, and 10 to the power of h minus 1 over h. Now, 10 to the power of x can come out the front, because 10 to the power of x is not going to change, because h is the one that's changing in this case. But again, what we try and do normally with our limits is try and find a way to be able to substitute 0 in by eliminating the h on the bottom. We can't do that in this case. There's no way we can eliminate that. So what we've got to do is, well, let's start looking at values as h approaches 0, and that's where I've used a spreadsheet here. There's my values of h when h is equal to 1, and they're starting to get smaller. They're approaching, h is approaching 0. And we get down to a pretty small number, but you can start to see that it starts when it's 1, it's 9, so it's not close to the number. But as they start to get smaller, you can start to see how the numbers start to change. Like we get to 0.2 and our 2 is the same. Get to 0.01 and we've got the second digit in place. And then we start to get the third digit in place, and so on. So what we're looking at is the number getting closer to a particular number. It's going to be an irrational number. So we're not going to get an exact value there. So we can only get an approximation if we're going to put as a decimal. What it works out to be is this number, natural log of 10. So natural log of 10 is 2.30258 and so on. So you can see it like at 5 decimal places here with the 1. We're getting closer. We're getting pretty close, but again, it's approaching 0. So what we can say is this number here will start to approach 10 natural log of 10. So the derivative of 10 to the power of x is the 10 to the power of x. That stays the same times natural log of 10. So that's where we get that. So if it's y is equal to 2 to the power of x, it would be 2 to the power of x times natural log of 2. If it was derivative of 3 to the power of x, it would be 3 to the power of x times natural log of 3. And that's how it works out. So what are these natural log values? Well, let's have a look. If you look over your page, and we have 10, natural log of 10, we just saw that there. We see natural log of 5, natural log of 4, natural log of 3, natural log of 2, and that we know from what we've done before, log, no matter what the base of 1 is 0. So the key here is looking at this part. At the situation where we go from having a decimal to something that's more than 1. So what we want to do is try and find that point that where we take the natural log of what number will give us 1, and that's going to be some number here. You can look and see that 3 is just a little bit more than 1, 2 is a bit less than 1, so it's 2.71828 and so on will give us something close to that. What that is our value of e. So our value of e is an irrational number. It starts off 2.71828, and that looks like it might have a little pattern for a while if you have a look at it. You've seen it plenty of times in the back of the classroom. We've got e to 10,000 digits there, but also you can find a value on a website. I think the world record is about 50,000 decimal places someone's remembered e to, so they still need to get a life. But that's where we get this. That's the value of e there. So e is that number. So if we're going to draw up our graphs, we know what an exponential graph looks like, hopefully. That we've got the graph 2 to the power of x, 3 to the power of x, e to the power of x is between those. So we can see that even e to the power of x is going to be treated like some other constant. E is a constant. It doesn't change. It's like pi. It's an irrational constant. So we've got these values. We've got the values here. The 2, the 3, the e. Said e is about 2.7. So it's a little bit less than 3. So the curve would be inside the 3, a little bit more than the 2. But again, you know what happens here, and that's what we hopefully realise, that we know that graphs all go through 0, 1. We know that as x approaches minus infinity, y would approach 0. What happens as x approaches infinity? Well, y gets approaching infinity as well. But what about the gradient of this curve? Now, if you go back to the idea of what we just did here, that's the derivative of 10 to the power of x, which would be 10 to the power of x times some number, which means the gradient function is also an exponential curve. So that's what's really important to bring out. When we describe gradients of exponential curves, they are also exponential curves. So that's the main thing we want to see. And as we said, like natural log of 10 times 10 to the power of x is just a constant times 10 to the power of x. So it has a multiplication factor there. And that's where e is going to be important. In our next video, we'll discuss what the significance of e in this case would be for our functions and their gradients.